Alright, this will be a quick covering of the section 2 of chapter 3 of the sequences and series. First off, just define a sequence. That's gonna just be a string of numbers. So you have like 1, 3, 5, 7, 9. And then a series would be 1 plus 3 plus 5 plus 7 plus 9. And then if you have an infinite version, so if you make this an infinite series that goes on forever, it can be placed in one-to-one correspondence with the integers, or positive integers, so there's going to be, that's going to go on forever, and the series is the same thing. This is going to be going on forever, and there's these also will be put one-to-one correspondence. Alright, so we have two different ways of defining the sequence. What we're going to usually start with is going to be looking at what the string of numbers is. For this, we'll do 1, 4, 9, 16, 25, 36. And this is pretty clear what this is. We see the first term, which will denote A1 is 1, A2 is 4, A3, 4, 5, A6. And so we can see here that A sub n is going to be equal to n squared. So how we can define this is by putting n braces, they say from n equals 1 all the way to infinity. You have a of n, and that's going to be equal to, in braces, n squared. Or more simply put, a of n equals n squared. So that's how you would define a very simple series by equation. And then if you want to define it by recursion, what we have to do is, first off, we have to say, define a equals 1. And the next step would be to define a n plus 1. And so a trick for this would be, okay, we see a to 1 to a to 4. So a of 2, or right, so we're gonna look at this. I'll put this down here. If you have a of 1 equals 1, a of 2 equals 4, a of 3 equals 9, and so on. You can write this as a of 1 equals 1, a of 2 equals 1 plus 3, a of 3 equals, or a of 1 plus 3, since we're recursively doing it, then a2 plus 5, and so on, if you see the pattern. So if you look, we can define this as a sub n. And we're looking at, let's say 2, so it's going to be plus. And then, what can we do to turn 2 into 3, 3 into 5, 4 into 7? All we can do is double it, and then subtract 1. Oopsies. Oh yeah, so if we're looking, oh no, add 1, sorry about that. Because if we're looking, we have plug in 1 for a of n, we got 1 plus 2 times 1 plus 1, that's going to be plus 3. Then we get 4, which is a of 1 plus a sub 1 plus 1, which is a sub 2. So we do an example, a sub 5 plus 1 is going to be equal to a sub 5 plus 2 times, or plus 2 times 5 plus 1. If we substitute this stuff in, we know a5 is going to be 25 plus 10 plus 1, so it equals 36. And if we check, that checks out. And we can also kind of go the other way if we start with if we look at this, it's much easier to see how this is defined recursively instead of how it's defined with a formula. And so we have a sub 1 equals 5, and if we look, a sub n plus 1 is always just going to be 5 less than the previous one, so that's just equal to a sub n minus 5. We can check this out. We can try a sub 4 will be equal to a sub 3 minus 5. Check this out, and 10 is in fact equal to, or negative 10 is in fact equal to negative 5 minus 5. But if we want to do this by formula, it's a bit trickier, and this will be more covered in the next video, which is over arithmetic series. But if we look at it, it's going to behave a lot like this is still going to behave a lot like a linear equation, because we can see we have, if we put this into y equals mx plus b form, we can plug in the slope right here as y equals negative 5x plus b, and then we can find the b as being some non-existent a 0 term, which if we follow the pattern of adding 5 every time we go down, we get 10. So it's going to be our b term would be y equals negative 5x plus 10. And so when we plug this in, we should be able to say this, I'll just diagonal equal sign because I already filled that area, should be equal to negative 5n plus 10 for n equals 1 to infinity. So check this out. Let's say we're looking for n equal a sub 4. Well, we plug 4 into negative 20 plus 10, negative 10. So this checks out pretty easily for these type of equations. And then the last thing I'm going to introduce is summation notation, which is a capital sigma. And what you do is you define your lower bound variable on the top and your upper bound at the, or lower bound variable at the bottom and upper bound at the top. If you put infinity, that just means an infinite series. Or you could also do something like n equals 1 to k. That means you're just going to do this series k times. So if we just, for example, if we did n equals 1 to infinity of 1 over 2 to the n, this would be equal to 1/2 plus 1/4 plus 1/8 and so on. Or if we did n equals 1 to infinity of just n, we would have 1 plus 2 plus 3 and so on. And if we want to do something k times, we could have a capital sigma n equals 1 to k, and let's just say we're doing n squared. We would set this equal to, this would be equal to 1 plus 4 plus 9 plus all the way to k squared. And if we want to practice evaluating something, we'll just, I guess, evaluate this series, but for k equaling 6. And so of n squared, that would be equal to 1 plus 4 plus 9 plus 16 plus 25 plus 36. And for now, before we've actually defined a function for this, we'll just add this up. That's 30, 55, 85, 91, I think. Two ways to double check that. But the general idea is you just do this function for each of those values of n. That should be it for the second section.